Okay. Now I will be discussing some shortcuts for drawing shear force diagram and bending moment diagram without actually solving it. Okay. So first we will see how to draw shear force diagram using loading diagram. To draw shear force diagram from loading diagram using loading diagram, first we have to know the relation. The load is nothing but the slope of the shear force, because when we differentiate any variable we will get slope, we know that. So d by dx of shear force is load, means load is nothing but slope of shear force. Okay. So using this relation we will obtain some shortcuts from this. Okay. So suppose if there is no load means the load value is 0, means the slope value is 0. So slope is 0 means you will have a horizontal line because slope is 0. So horizontal line means you can have a 0 shear or you can have a rectangle also. And second, if you have point load. So point load means the value of x will be 0 because the point load will be concentrated. So that is why the x value will be 0. So when the x value is 0, the load value will become infinite, which means that the slope becomes infinite. So slope infinite means it is a vertical line. The load value will become infinite, so that is why slope is infinite. So you get a vertical line because slope of vertical line is infinity. Suppose if you have a UDL. UDL means it is a rectangle, it is similar to rectangle. So here you can see UDL, so it looks like a rectangle. So if you have a UDL, which means that the value of the load is constant throughout the length, which means that you will have uniform slope throughout the length. So you will get a triangle in shear force diagram. The load value is uniform, so the slope is uniform. When the load increases, the slope increases. When the load decreases, the slope decreases. As there is a uniform load here, you have a uniform slope here. Okay, we will solve some more examples on this anyway. Next, suppose if you have a triangle in the loading diagram, then you will have a 2-degree parabola in shear force diagram. So suppose if you have a triangle, you will have a 2-degree parabola in shear force diagram. Okay. Now we will see examples to apply all this. So if there is no load, then there is a 0 shear or rectangle, and if there is a point load, there is vertical line. Let us see. So consider this loading diagram. I am telling the shortcuts to draw the shear force diagram from left to right. Okay. So from left I am starting. So here my shear force is upward. So that is the reason RA upward. So this is my reference line. So I have drawn RA upward. Now in this zone there is no load. So when there is no load, you should have a straight line, 0 shear or rectangle. So there is no load in this region, so slope value is 0. Again there is a point load W downward, so I will get shear force downward. Again there is no load, again reaction upward. So upward 0 shear, downward 0 shear, upward. So you can see that is the answer. Next we will see cantilever. So for the cantilever, the reaction moment I have drawn on the right side. Generally we will draw the moment on the left side. Why I have drawn this on the right side, I will explain this in structural analysis. This is the best way to represent the reaction moment, while I will explain in structural analysis. Okay. So when we apply the load W, the reaction we get is W. Okay. So I am starting from left to right. So starting W upward, no load, so horizontal, W downward, so W downward. Okay. Now in this case, when there are two moments, the reaction value will be 0. So here there is no load from the beginning, so straight horizontal, 0 shear force. Suppose if there is a couple like this, you will have minus M by L. Minus M by L means the assumed direction is wrong. So you will get the value actually downward. Okay. So minus M by L, here you will have plus M by L. So minus M by L means you will have downward load. So you will have downward, there is no load here, straight, and again there is, so here you will have plus m by l, which means upward. So downward, no load, upward. So this is the shear force diagram. Okay, so I hope these two are clear. Now we will see the rectangle case. So here is the rectangle. So first we will have reaction upward, upward. Here there is a rectangle. So if there is a rectangle, the shear force will have triangle. So this is a uniform rectangle. So this is also uniform triangle, because the load value is same means the slope value is same. If the load value is increases, slope value is increasing. If the load value is decreasing, slope value will decrease. So upward, triangle, triangle, and then upward. So upward, triangle, and then upward. We can see here. So similarly we can see here also. So when there is a load here, we will have a reaction and also we will have a moment here. So reaction, and there is a uniform load downward, uniform slope downward. So here also you have load downward, that is why I have drawn this downward. Suppose if the load is upward, I would have drawn upward. So the load is downward, so uniformly I have drawn downward direction. Here the load is upward, so I have drawn upward. So here start from up and then down. That's all. Next, the fourth case, if you have triangle in the loading diagram, in the shear force diagram you will have a 2-degree parabola. So if you have a triangle here, so first upward we know. Next, if you have a triangle, then you will have a 2-degree parabola. So that is the reason. So from here to here we can see the load value is downward, which means that it is a falling parabola. From here to here the load value is downward, so it is a falling parabola. So throughout the reason the load value is downward means, everywhere downward means throughout the length the parabola will be falling continuously. Here also we can see the load value is downward throughout means it will be falling continuously. So here it is a triangle and it is falling means it is a parabola and it is falling. So initially we will have a reaction upward and then falling parabola and then reaction upward. Same here also we can see. So when there is a loading diagram, obviously we get a reaction here. So we get a reaction and it is a falling parabola because the load is downward. So I have drawn a falling parabola like this. Okay. Now in the exam, suppose if they give convex parabola and concave parabola sometimes, how to identify whether the answer is convex parabola or concave parabola without solving, how to identify this. Okay. So I hope you are clear with all these examples for the 4 cases: no load, point load, rectangle and a triangle. Suppose if you have a 2-degree parabola in loading, then the shear force will be 3-degree parabola. 2-degree parabola means y is equal to mx square plus c format. 3-degree parabola means y is equal to mx cube plus c. The 3 value or 2 value is called degree of the equation. Okay. So next we will see how to identify whether we are going to get a convex parabola or concave parabola. Now we will see how to identify whether we are going to get a convex parabola or concave parabola in the answer. Okay. So here you can see the 2-degree parabola curve, y is equal to mx square. So here what is the value of y? This is the value of y. So we can see the y is equal to mx square is a, so we can see this is the convex side and this is concave side. So you can observe clearly. So this is the parabola. So in this side, if you draw this parabola, we will look convex. If you draw this parabola, it looks concave. So actually our y is equal to mx square, whatever we are drawing is concave. So when we will get convex also, let us see. So suppose if there is a UDL for me, okay, so then we know that the shear force diagram will be a triangle and it looks like this. Suppose if it is triangle, then we know it is 2-degree parabola, but we do not know. So this is a loading diagram. So we know the answer is going to be a 2-degree parabola, but we do not know, and we also know that it is a falling curve. So we know we have to draw a parabola that is falling. There are two ways to draw this. We can draw like this, and also we can draw like this. So both are 2-degree parabolas and both are falling curves. So in this, which will be my answer? How to identify that means? So suppose if you see here, when we are adding the loading diagram, the equation comes like y is equal to wx square by 2. Okay, so whatever the load we are calculating, it comes wx square by 2. So we need not what is the constant here, we don't require. It comes in the form of y is equal to mx square. When it is y is equal to mx square, we will have a parabola that is concave. So this is my answer. Okay, now we will see when we will get this. Okay. So now see this loading case. So in order to find the area of this, you can take the values from here also. So here there will be a moment and there will be a reaction. Okay, so to know the shear force at any point, so the equation looks like r minus wx square by 2. So whatever it may be the value, so half of base into height, wx square by 2. So it looks like it is not y is equal to mx square, it is some constant minus mx square. So some constant minus mx square means what happens, let us see. So we have seen this is y is equal to mx square, and this y is equal to mx square has to be removed from a constant value. Let us remove that. So this is y is equal to mx square curve. Take a constant value c and remove y is equal to mx square from that constant. So we have to remove this y is equal to mx square from the constant value, c minus y is equal to mx square. So the remaining parabola will be this. So the answer is a convex parabola. So if you are getting the equation as y is equal to mx square format, the answer will be concave. If you are getting the equation like c minus mx square, the answer will be convex. You need not find what is the value of reaction here, just you have to identify how the equation is going to come, that's all. So then you can find whether it is convex or concave. So here the answer will be, so we know the load is falling here, clearly we know that the load is falling here and it is a triangle. So my answer is a parabola falling convex. So the answer is falling parabola convex like this. So previously we have seen that if you reverse the triangle like this, we got the answer as, because it is y is equal to mx square, so it is concave parabola. It is c minus, in this side also we can see, we cannot write y is equal to mx square, because if you find the area of this, it is a trapezium, half h into a plus b. So you won't get y is equal to mx square format, you get some constant value definitely. In that constant you will have this w value. So that is the reason we are getting a convex parabola here. Okay. So when the loading diagram, in the loading diagram, suppose if there is a no load, if there is a point load, if there is a UDL, we can draw it very easily. So suppose if there is a triangle, then by observing the triangle we should be able to guess whether we are going to get a convex parabola or concave parabola. So by seeing the loading diagram we can know whether you are getting a falling parabola or rising parabola. It's very easy. So suppose if you take a cantilever and if you draw, if you have a load upward like this, and suppose if you have a load downward like this, then we will get some reaction here. So when we are drawing from left side, so here we can see it is upward, there is no load, here there is downward, so it depends on what is the amount of load we are using. So how much down it will come depends on what is the load here, and then there is no load, and then upward, like this. Okay, so in this way we have to start from the left side. So if the load is upward, draw upward. Then if there is a falling load, draw falling. If there is no load, draw a straight line. If there is a point load, draw a vertical line. Again, if there is a point load, draw a vertical line. So in this way we can draw shear force diagram of any type of loading diagram, and observe that if there is a couple, so we have seen this example also. So if there is a couple, so minus m by L plus m by L is the reaction. So we have seen that at the point of couple there is no effect for shear force diagram. So once we find the reactions, you need not consider this couple while drawing shear force diagram. It won't affect the shear force diagram. So even by seeing the shear force diagram, we cannot identify whether a couple is present in the loading diagram or not. Okay, so that is important point. So with this, the shortcuts for shear force diagram is completed. Next we will see how to draw bending moment diagram. Okay, now we will see how to draw bending moment diagram. So for that, the point which we have to remember is, previously if there is a concentrated point load, we will get a vertical line in SFD diagram. Similarly, if there is a couple, then we get a vertical line in bending moment diagram. So that point we have to remember here. Now we will see how to draw bending moment diagram after drawing shear force diagram. Okay. So suppose if this is the loading diagram, so first we will see how to draw shear force diagram. So I will start from the left side. So here I will get the reaction RA, here I will be getting the reaction RB for whatever the load W. So the reaction is upward, I have to start from left side. So upward, no load, horizontal, downward load, no load, horizontal, upward. So here also SFD, upward load, UDL, so it is a falling triangle, and again upward reaction. Okay, so we have drawn the SFD diagrams. Now we will see how to draw BMD diagrams from this. So to draw BMD diagrams using SFD diagram, I will tell you one shortcut, so which is very useful. So here we can see the shear force is positive, here we can see the shear force is negative. So here also we can see the shear force is positive, here the shear force is negative. Okay, so here the shortcut is, suppose if the shear force is positive, then the bending moment is increasing. So remember that if the shear force is positive, then bending moment is increasing. Okay, so you have to draw from left side. Okay, remember that. So if the shear force is positive, the bending moment is increasing. Okay, so when you have no load here, then you will have rectangle here. If you have rectangle here, here you will have triangle. If you have triangle here, then you will have 2-degree parabola here. Similarly, if you have a rectangle here, in bending moment you will have triangle. If you have a triangle here, in bending moment you will have a 2-degree parabola. If you have a 2-degree parabola here, then you will have 3-degree parabola in bending moment diagram. Okay, so that we have to remember. So now, as there is a rectangle here, in bending moment we will have triangle. So that we know. So how to draw the triangle means, when the shear force is positive, we can see the bending moment is increasing and it is a triangle. So it is increasing triangle till this point. Now here we can see the shear force is negative, means it is a falling triangle, because there is a rectangle here. So you will have a triangle that is falling. That's all. So this is your answer. Okay, so similarly we will see here. So here we can see, in shear force you have triangle, means in bending moment you will have parabola. So here shear force is positive, so don't see whether it is falling or rising. We have to check whether it is positive or negative, that's all. Whether it is falling or rising, that doesn't matter. So if the shear force is positive, bending moment is rising and it is a parabola. Bending moment is rising and it is a parabola. So here it is negative, so bending moment is a falling and parabola. Bending moment is a falling parabola. Okay, now we will see some more examples on this. Okay, now we will see some more cases to draw shear force diagram and bending moment diagram. So first here, if there is a load, we get a reaction. So to draw shear force diagram starting from the left side, so here you have upward, so draw upward, no load, horizontal, falling load, falling. So here there will be a reaction, it is a rectangle, so here you will have triangle, that is falling. That's all. Next, if there is a moment here, we get a moment here, that's all. There is no reaction here, so zero reaction. There is no load, so horizontal line, that's all. So if there is a M here, you will have minus M by L reaction and plus M by L reaction here. So as it is minus, we have to draw downward, no load, upward. Okay, this is M by L. Okay, so we have drawn the shear force diagram of all the cases. Now we will draw the bend moment diagrams for this. So initially we have to start from left to right as I said. So here we can see there is a moment here. Okay, so generally I used to draw moment here on this side. So there is a moment here, so we get a vertical line here of whatever the value of M. Reaction we need not find. Now here we can see the shear force is positive rectangle, which means that in bending moment I will have a triangle that is rising. Okay, so this is my BMD. So why I got this on the bottom side means in cantilever we will have hogging, in simply supported we will have sagging, so that is why I got bending moment on the top side. In simply supported I got bending moment on the bottom side because this is a cantilever. So similarly, so initially I have a M value, so I will get a vertical M because the first what I said, if there is a concentrated couple then you will get a vertical line. So this is the vertical line. Now this is positive, it is looking positive, we can see. So you will have a parabola. So this parabola, whether it is convex parabola or concave parabola means, see the equation. So it is looking like wx square. So it is concave parabola. It is a concave parabola. So suppose if there is a moment here, then you will have m minus wx square. Suppose if you have a couple here, you will have m minus wx square. So some constant minus wx square, then you will get a vertical line and a convex parabola. So here there is wx square by 2, so that is mx square format. So we are getting a concave parabola. Okay. Now we will see this case. Shear force is a straight line. So in bending moment, so there is a couple M. So I can draw from left to right or right to left. So there is a couple M. So there is no shear force. So straight line and again M. So next for this case we can see it is negative shear force and it is a rectangle. So you will have a falling triangle here. Okay. So starting from left, falling rectangle. If there is a concentrated couple, then you will have a vertical line in bending moment diagram. So after this point also it is negative, so still it is a falling. So this is the BMD. Okay, so if there is a concentrated couple, then you will get a vertical line. So here also there is a couple, so here also you have vertical line. Here there is a couple, there is vertical line. So if there is a concentrated couple, then we get a vertical line, and if you have no load here, then you get a rectangle here. If you have rectangle here, then you will get a triangle here. So if there is rectangle here, you will get triangle parabola. So if you have triangle here, you get 2-degree parabola and then 3-degree parabola. If you have a 2-degree parabola here, then you will get 3-degree parabola, here 4-degree parabola, and so on. So I hope drawing bending moment is clear. Now we will see some more examples to draw shear force diagram and bending moment diagram without actually solving it. Now we will see a complex loading case with UDL and moment, falling load and rising load, everything. So I have included all the case. Once we solve this problem, we will be able to know how to solve SFD and BMD. Okay. So starting from left, so there is a rising reaction. So I do not know what is the reaction value. So approximately how it is going to come I can figure out. So here there is a upward load. So draw upward. So here there is a falling load and it is a rectangle. So you will get a triangle here. Okay. Now there is no load here. So I will get a rectangle here. So again there is a point load here. So it is rising. So here there is no load. So it is uniform till here. Again there is a falling load here. There is no load here. Again there is rising point load. Okay. So approximately the shear force diagram will come like this. I do not know any values for this. I did not give any. So approximately how it is going to come, I have figured out it. Now I will draw bending moment diagram by seeing the shear force diagram. See. Now to draw bending moment diagram, so here I can see this is positive, negative, positive, negative. So it is positive means bending moment is rising. It is triangle means bending moment is a parabola. Now to draw the parabola, whether I have to draw a convex parabola or concave parabola. So for this we can see, to find bending moment diagram, it is reaction into x minus double x square. So it is something minus double x square, which means that it is a convex. If there is nothing here, then you will get concave. So here there is something like reaction into, so we will be getting convex here. So draw a convex parabola in this zone and it is rising till here. Okay. So till here only it is rising because till here it is positive. Next, from here it is negative, falling means it is a falling parabola like this. So here also it is negative, but it is a rectangle. So if it is rectangle, it means that it is a falling straight line. So this is parabola. So this is a parabola till here like this. So here you have a rectangle and a negative means you will have a triangle and falling because it is negative here. So till here it is falling. And again you have a positive rectangle here, which means that you have a rising triangle here. Okay. So here you can see there is a concentrated moment here. So which means that you will get a vertical line here. So here you have a moment here. So you will get a vertical line here. After this point also it is still positive. So it is rising. And from this point it is negative rectangle means it is falling triangle. That's all. This is the answer. Okay, so I will explain this example again. So first, drawing the shear force is very easy. So upward load, as it is concentrated load, draw upward. Then it is UDL. So falling. There is no load, straight line. Again rising load, upward. There is no effect of moment while drawing shear force diagram, as I said. So there is no load here, straight, falling load downward, rising load upward. That's all. So from this, how to draw bending moment diagram. So remember that wherever there is a concentrated load, you will get a vertical line at that point in bending moment diagram. Okay. So this is positive triangle. So you will get a rising parabola till here, till this point. So it is a rising parabola till this point. In this zone, if you concentrate, it is a triangle and negative, means it is a parabola and falling. Next, in this zone, it is a rectangle and negative, means it is a triangle and falling. Next, in this zone, it is rectangle and positive, means it is triangle and rising till here. Now remember that if there is a concentrated moment here, then you will get a vertical line in bending moment diagram. Now here also it is a positive rectangle, so it is a rising triangle. Again it is a negative rectangle, so it is a falling triangle. Okay. So you can see here, so triangle, parabola, triangle, parabola, rectangle, triangle, rectangle, triangle, rectangle, triangle, rectangle, triangle. Okay, so positive, rising, negative, falling, positive, rising, negative, falling. So when there is a couple, you will have a vertical line. Okay, so in this way, we can draw SFD BMD of any loading diagram without actually solving it. Okay, so now you can select any textbook with adequate number of examples for SFD and BMD. So without solving, just observe the SFD and BMD. You will be able to understand it quickly, and you can finish each example within 1 or 2 minutes. Just by looking, you can identify the shear force diagram and bending moment diagram. So I hope this trick is very useful for you. Now I will explain you. We have seen till now what is positive bending moment, negative bending moment. We have seen this. So what does it actually represent is, so in shear force, the positive bending moment and negative bending moment says whether it is clockwise shear or anti-clockwise shear. That do not have much importance for us now. Here in positive bending moment and negative bending moment, the positive bending moment means it is a sagging moment. Okay, so previously we have seen for cantilever with point load, the bending moment diagram is negative triangle. Okay, so with the moment W into L. And for simply supported beam with point load, we have seen the bending moment is a triangle again. Okay, now cantilever doesn't mean that always you have to get negative. Suppose if the cantilever is subjected to a upward load like this, then we will get the bending moment as positive triangle. Okay, so where do we get cantilever and sagging means? Footing. Footing is an example for this. So suppose if you observe the footing, so the bearing pressure from the bottom of the footing, due to this pressure, this will act as cantilever. So this cantilever is not in hogging, we can see this is in sagging. And previously we have seen a special case of applying a moment. Okay, so here the bending moment is 0, simply supported. So previously we have seen that the bending moment will increase continuously like this. So this is in hogging portion, so it is negative here, and then bending moment M, and then 0. Okay, so whatever the couple we have applied here, so that couple value will be there here. Okay, so here on this side I have drawn negative, on this side I have drawn positive, which means that this is in hogging and this is in sagging case. Okay, so here this is negative means it is in hogging, here this is positive means it is in sagging. So here also it is in positive, it is in sagging. So how to find whether a beam is sagging or hogging? We try to find whether it is sagging in hogging to place the reinforcement. So suppose if it is sagging, we place the reinforcement at the bottom. If it is hogging, we place reinforcement at the top. Anyway, I will be explaining this in detail in concrete structures. Okay. Now, how to identify this whether it is a hogging or sagging curve means, first try to find how the beam is going to deflect. So when you apply the load like this beam will deflect like this. This beam will deflect like this. And this beam, so you can see this is rotating like this, which means that it will deflect like this, and here it will deflect like this. Now in order to find which is in sagging and which is in hogging, I will tell you one small shortcut here. Join any 2 points on the curve, any 2 points. So if the curve is above your line, then it is in hogging. So here also join any 2 points. So the curve is below means it is in sagging. So here also draw any 2 points. The curve is below, so it is in sagging. So here you can see the curve is above, so it is in hogging. The curve is below, so it is in sagging. So in this way, if you are able to imagine how it is going to deflect, then you can find whether it is in hogging or sagging. So accordingly you can draw whether it is positive or negative. So in that way also we can draw positive or negative bending moment diagram. Okay. To show these deflections practically, I have to take an element and show you the deflection. So to take a structural element to show you the deflection, I should be able to bend it so easily, which means that it should have less flexural rigidity. And another thing is, it should be a ductile material. So if I am selecting a brittle material, if I deflect it, it will immediately break without showing you the deflection. So to show the deflection, I have to select a material which has less EI by L value, and it should be a ductile material. Okay. So which means that I can select less E value or less I value or more L value. So what does this mean is, suppose if the length of the bar is increasing, the bending strength will get reduced. Okay. So how we will see that anyway. So now to prove this example, I am using a small structural element. So here you can see a steel spoke here. So don't think this is a cable. You can see it is acting as a beam, not as a cable. Suppose if you increase this length continuously, as you are increasing this length, as this is steel, steel has very good E value. So because of more E value, this is able to act as beam instead of cable with lesser amount of length only. Okay. So now we can say this is a beam. Suppose if the length of this steel beam is increasing, then it will behave as a cable. So cable bridge is an example for us. So in cable bridge, the length of the steel wire will be very long. So it behaves as a cable, not as beam. So similarly, if you take less E value, the material which has less E value, then it will automatically behave as a cable even at lesser length. Okay. So that is how we have to choose. So I have to choose a ductile material with less E value or less I value to show you the deflection. Okay. Suppose if I have taken a steel with more I value, I cannot bend it so easily. Suppose, so if I have taken a steel rod like this, I cannot bend this easily to show you the deflection. Even though it is a ductile material, it requires more load because its flexural rigidity is more. I cannot bend this so easily because this I value is more for this, E value and L value is same for this and previous, but because of more I value, I am unable to bend this. So that is the reason I will select a small I value so that I can bend to show you the deflection. Okay. Now I will show you what is sagging. Okay. So this is sagging in case of simply supported beam. So this is a simply supported beam supported on both the ends. Now if you apply the load, it will deflect like this. Similarly, for simply supported load, if you apply the load upward, then it is in hogging. So simply supported doesn't mean that it is always in sagging. Due to gravity loads, it is in sagging. If there is any upward load, then it is in hogging. So similarly, if you take a cantilever and subject to point load, then you can join any 2 points on this curve, you can see it is in hogging. Similarly, the same cantilever, if you subject to upward load, then it is in sagging. Okay. So I have shown you all these cases. Now we will see this case. Okay. So if a couple is applied, what happens? So if a couple is applied at the center like this, so you can see if a couple is applied, this part you can see it is in hogging and this part you can see it is in sagging, because if you join any 2 points this side, then the beam is below the curve is below the line. So if you join any 2 points on this side, then the curve is above it. So this part is in hogging and this part is in sagging. Okay. So this is the way I have selected the material to explain this example. There is another way to do this. I can take more I value with less E value. So for this, I have made with sponge, because sponge have very less E value. I can bend it very easily even though cross section is very much high. Okay. So this is simply supported with gravity load, simply supported with upward load, cantilever with point load, and whatever the final case we have seen, I will show you here. Okay. So moment, you can see if you apply moment, it behaves like this. Okay, so when a particular loading case is given to us, so depending on the loading case, you should be able to predict how it is going to deflect. So once we know the deflection curve, we will be able to find whether it is sagging moment or hogging moment. Okay, so I hope this concept is clear for you. Now we will solve one previous gate question, so whether our concepts are applying properly or not. Now we shall see some previous gate questions. Okay, so one question from 2003 gate and one question from 2009 gate, both are 2 marks question. We can see it is a match the following. So apart from this, still there are many questions which you can solve by yourself. So as a model, I will solve this. So here in the gate question, so one question is based on bending moment diagram and one question is based on shear force diagram. Okay, so for both example I have taken 2003 and 2009. So this is the figures given, match the following. So for bending moment diagram, first one, if there is a couple here, then there should be vertical line at the center. So from this option I can say this should be 2, obviously. And for this, we know the bending moment diagram is going to be a triangle, this. Next, this is a UDL, so the bending moment diagram is a parabola. Okay. So they have taken sagging as negative, we can see. Generally, we should take sagging as positive. But for this case, they have taken sagging as negative. That is the reason that we are getting negative here and also here. But practically, always sagging should be taken positive. But for this question, as they have taken negative, I am applying negative. Okay. So next, so here you have triangle, which means that you will have a 3-degree parabola in the answer. So the answer is this. Okay. So the answer should be 2, 4, 1, 3. So option D. So option D is the right answer. So this is how we can solve the question. Okay. Next, gate 2009 shear force diagram from loading diagram. Okay. So here we can see the loading diagram. So the loading is downward and this is rectangle, which means that it is a triangle falling. So it is a triangle falling. We can see here it is a triangle falling, and then there is a reaction here. There is a reaction here. There is a falling triangle. There is no load here. There is a horizontal line in this zone. So for this we can take this. Okay, we'll take this like this. Okay. Next, there is downward load. Next, there is upward reaction. Next, there is downward. Again, there is upward reaction. Again, there is downward. So here we can see this. There is downward, upward, downward, upward, downward. So which means this is going to be answer for this. Okay. Next, we will see this. Throughout it is UDL, which means that throughout the answer you will have triangle. So answer should be this. So throughout this is falling, falling, again reaction rising, rising, again falling, falling, again reaction rising, again falling, falling. Okay. So for this the answer should be this. Okay. And final one we can see this is falling, again rising, again rising, again falling. So falling, rising, again rising, falling. So this should be answer. Okay, so we can see the answer should be 3, 1, 2, 4. So option A is the right answer. So this is the way, without solving anything, just by looking at the options itself, we can solve the problems. Okay. So after this, so you need some practice to apply these tricks practically. So open any textbook with enough examples of shear force diagram and bending moment diagrams. So once you see more number of examples, so just within 1 or 2 minutes you will be able to identify the correct picture. Okay. So I hope these concepts are clear for you. Still there are some more gate questions on this concept. I will be explaining you that in shear force diagram and bending moment diagram in my strength of materials lecture. This class is only for the shortcuts for your competitive examinations. Okay. So I hope you like this video. Thanks for watching.